Hello, my name is Berend Smit, and we continue in this video our search for algorithms that can do molecular dynamics simulations at constant temperature. And the Anderson, from Hans Anderson from Stanford, was one of the first algorithms that correctly sampled the canonical ensemble. And it's a very interesting one because it's a very robust one. It always works. So what is the idea of a Anderson thermostat? So what we have is, this is our system, our particles, and you see the arrows are indicating in which direction the particles move. So what Anderson thought, the way we can mimic a thermostat is we introduce a daemon, and we'll just call it here the Anderson daemon. And what this daemon does, it is at random moments during the simulation, it takes a particle and it gives the particle a new velocity taken from the Maxwell distribution of velocities at that particular temperature. So what is then the idea in the algorithm? You select a particle at random, you have this particle, and then you give this particle a new random velocity from the corresponding Maxwell distribution, that corresponds to the temperature you would like to simulate. So this is the velocity distribution that depends on beta, the particular temperature we're interested in. So, and what we then assume is that the probability that such a collision occurs, that or collides with what we call with the Anderson daemon, that it gets that kick, is given by a Poisson distribution. And this is the Poisson distribution that basically tells you that all the events are uncorrelated and they simply depend on on this value v, which is basically the time between the average time between collisions. So every particle has its own Anderson daemon that once in a while gives this particle a new velocity taken from the Maxwell distribution. So the reason this method works by construction is that it basically imposes the right distribution. So if for one way or another the system heats up, by the subsequent collisions, we remove the energy or we add kinetic energy to the system depending on what's going on. So this is really a very rigorous way. But you can see it has also its consequences. So this is then a typical algorithm, which would be the notion of an Anderson thermostat. It looks very similar to our basic MD. The initialization, we calculate the force, we integrate the equations of motions, and we do the sampling. Of course, whereas the difference is in the way we construct this collision with the Anderson daemon. And that is sort of shown here. So here we integrate the equations of motions. And it's interesting to see that in this particular case, we do use the velocity-Valère algorithm as is coming out of a Trotter expansion. So here, you do see the situation. So we have a switch here that tells whether what to do. So what you see here, if the switch is equal to, then we have this loop in which we select a probability, in which we have here this probability that we get this collision with the Anderson daemon. And then we take the new velocity from a Gaussian distribution. So otherwise, you just update the velocities normally using the velocity-Valère algorithm. You see we do that here, but here, if the switch is set to 2, we do here in this part, we check whether after so many time steps it is time for the particle to collide with the Anderson thermostat. And what it does, it gives this particle a new velocity from the desired Gaussian distribution, the distribution corresponding to the Maxwell distribution of that corresponding temperature. So here we make sure that the temperature is correct. Okay, so and what you see here is an example of the Lennard-Jones fluid where we have implemented this algorithm. And this is the analytical equation from the Maxwell-Boltzmann distributions, which we need to sample. And you see how we get the correct fluctuations. And you see it doesn't have, so this is this collision frequency with the Anderson demon. And you see this velocity distribution doesn't depend on the frequency. What we can also do, and here we see the equation of state, and we see also the density. So this is an isotherm. You see how the pressure changes as a function of the density, and whether we use Monte Carlo molecular dynamic of the equations of state, we're spot on. So from these properties, from the static properties, there is no issue. However, we can also look at the mean square displacement. And as you know, the mean square displacement is something that is important to compute a diffusion coefficient. So what we then typically do, so this is time, so we look at the slope, and from the slope we get the diffusion coefficient. And what we see is that diffusion coefficient here depends on the frequency at which we get a collision with this Anderson demon. And that is, of course, to be expected, because if you get many collisions, we perturbing the natural dynamics so much that we cannot get a correct diffusion coefficient. And that is actually very important, because this Anderson thermostat, what we do is we select a particle at random, we give that particle a new random velocity from the correct distribution. But that is not the intrinsic dynamics of the system, that is completely perturbed. So in fact, this Anderson thermostat, or any thermostat that does artificial sort of things with the velocity, is very dangerous to use to compute dynamic properties. So here we see an example of a dramatic effect, and of course these frequencies are a little bit exaggerated. Normally you would do a much smaller one. But if you want to calculate dynamic properties, it's much safer to stop using the Anderson thermostat once it's equilibrated, and then just do an NVE simulation using a conventional molecular dynamics. At least then we don't influence the dynamics, and that is sort of an important result. So what we have seen is that the static properties, like we have here the equation of state, you can use any value of nu, and there's no dependence that you can see. However, for the dynamic properties, we have to realize that we artificially change the dynamics. So we in fact should not use these algorithms to compute transport properties.